Hey guys, it's Professor Goodman. Um, this week's homework is there's a little more going on, so we're getting into probability, and it can take a little bit of time to get used to uh, how to do probability problems. They can be uh, require a little bit of out-of-the-box thinking, but once you get some practice, hopefully it'll become a little easier. And I'm also hoping that this video can help maybe ease your way into some of the probability explanations can get pretty difficult, but hopefully watching me work through these problems and then you doing them on your own, hopefully this will help you guys out some. Okay, so pulling up the homework, starting in chapter 6. So there's for this one there's three. There's three due homeworks that'll be due not the Wednesday of your test, but the Wednesday after test week. So next week's Wednesday, not this current Wednesday. You'll have three eMaths due. So quite there's a little bit going on here, but hopefully it all ties in together fairly well. So once you start getting into the swing of things, possibly it won't be as difficult. But first things first, let's get into some pretty basic uh, probability problems. So reading this out says, you're playing a board game with your friends that uses a six-sided die. Over the course of the game, you roll the die 66 times, 12 of which are twos. You win the game, but your friends are competitive and accuse you of cheating. That's not good. Which of the following statements are true? Okay, so it's a six-sided die, right? So going by the empirical rule, or our theoretical probability, or empirical probability, all of them should suggest that approximately with 66 times, each of these numbers should appear approximately the same number of times, with give or take a few, right? So we should have a approximate uniform distribution across all of the possible outcomes. Now, of course, sometimes if you have really, really bad luck and you roll a six-sided die, maybe you could get 20 ones or 30 ones with a fair-sided die, but chances are probably not. So if you're rolling this 66 times and 12 of them are twos, how much exactly is that? So let's do 12 divided by 66. Okay, so about 18%. So doesn't seem like it's way too out of the realm of possibility. So let's see what approximately each side should see. So if we know we roll it 66 times and there's six sides, do this. So this is 66 divided by 6. So approximately around 11% per per number. So each number should occur roughly about 11 times each, right? So 6 will appear around 11 times, 5 will appear around 11 times, and so on. So 12 times we have the number 2. So 12 isn't way too far away from 11, right? So then which of these options seems the most likely? So we can say the die is likely fair. We don't really know this for sure. I mean, it could be that the die is not fair, but we don't have enough evidence to really support this. And we don't know if we can say the die is likely unfair either. These two are kind of the crazy options that you shouldn't go with. But down here, these two seem more reasonable. Given a fair die, theoretical probability suggests that each number 1 through 6 would be rolled 11 times. Now this is a good time to know the difference between theoretical probability and empirical probability. Empirical probability is kind of like hard evidence. So once you go through it enough times, it would be like hey, I rolled a die 300 times and the number 5 showed up, I don't know, 40 or 50 times. So that would be something empirical. Theoretical sounds exactly how it is, right? It's you um, you do what we kind of did, right? So when I calculated the 66 total different rolls by 6 different sides of a die, I got 11. So theoretically, each number should pop up 11 times. But we know empirically, uh, the number 2 occurred 12 times. So we should say that this one seems like it's okay, but we got to go with the most right statement. It says if the empirical probability does not match the theoretical probability, the die is unfair. No, that's not cool. So let's go with this guy. Because see, the empirical probability does not match the theoretical probability, the die is unfair. That is definitely not true, because like I said, here our empirical was 12 and their theoretical was 11, but still, that doesn't mean it's unfair. It's close enough. So that would be that first one. The rest of these problems are pretty simple. They're just basic probability problems. So like this one here, tiles numbered 1 through 16 are placed in a bag. Let A be an event that one tile removed at random is a prime number. What is the probability of A? Okay, well this one you just have to simply count. Well, how many prime numbers are there between the numbers 1 and 16? So let's see, let's just draw them out. So 2 is a prime number. Now remember, a prime number is defined to be a number in which its factors are only 1 and itself. So 2, well, only 1 and 2 are factors of 2. And then 3, right? So just keep going. 5, 7, 9, 11, 13, and that's it, right? So 2, 3, 5, 7, 11, 13. So if you want to count these, simply highlight all of these, and you can look down here and it says count is 6. Now, of course, if you want to, you could also do this, count, you use a count function, which will count all the numbers you have there for you. So there's 6 prime numbers. So in other words, here it says what's the probability? So we have 6 divided by 16. So we put 6 divided by 16, or you can reduce this. This would become 3, and this would become 8. So 3/8. And that answer is correct. Okay, and this one is just a concept question. It just says, hey, you got some kind of nerdy friends playing Dungeons and Dragons. That's the kind of stuff I like to do. Say, oh, you try all these experiments to see whether or not these dice are fair. I don't know why you have all these friends that don't trust you, but I don't know, it's statistics. So all these guys ask you to, or try to roll your die to make sure that they're fair, but they're actually testing it. So they're seeing, they're testing it themselves to see if they are fair. So this would be an example of empirical, right? Because you're actually testing it. Theoretical would be they calculate it through theory, so not, or calculate it with like formulas and such, which they didn't do. So then that is definitely empirical. So the rest of these kind of follow suit, the probability problems and so on. And then this one can get a bit tricky. Well, anytime you have a lot of problems that have this much to read, typically that's not all that fun. But basically the gist of it is Plinko is you just drop a ball down one of these slots, and you're hoping to see which slot would give you the best chance to win the $10,000. Because you don't want to win the $0. 1,000, 500, 100, while that would be great, 10,000 would be the best. So what's happening is they say, okay, we're going to drop 270 total discs, and they were dropped equally between each slot. And now they say there's 9 different slots, so 1 through 9. So first off, it says if they're dropped equally between each slot, let's figure out how many discs are dropped in each slot. Okay, so let me kill this. Okay, so they say 270 total, right? That's how many they said were dropped total. So that'll be our total. Now, how many are per slot? Okay, well, they said it's evenly, so it would simply be 270. So your 270 total disks divided by 9 slots, right? Because they said there's 1 through 9, so there's 9 slots. And now sometimes counting the different outcomes can be kind of hard. Like, what if there was 1 and like 1,000 slots? You might be like, oh, well, that's just do 1,000 minus 1. Kind of. You gotta keep in mind that when you're doing these counting problems, you have to count the first and the last number. So if I were to give you numbers 1 through 10, how many numbers would that be? Well, remember, if we calculate the range is your max minus your min, right? So if I do 10, so equals 10 minus 1, then the range would be 9. So that's how many total numbers I can expect. But that's not how many numbers I actually have. So like if I count through this, let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now how many numbers is this? Let's have Excel count it. So equals count. 10 numbers. So even though the range is 9, we have 10 total numbers we can choose from. So that's why whenever you're doing these counting type problems where you have to like count like I don't know, the numbers 1 through 100 are used in some kind of gambling ball game or something, and you want to try to identify probabilities in that. The best thing to do would be to take your range and then add 1 to it. So this will give you all of your values. So just like here, we have numbers 1 through 9. Well, this doesn't mean that there are 8 numbers. It means we have 8 plus 1. So then we have 9 total slots, right? So that's just what I'm saying. So we have, that's why I did this 270 divided by 9. All right, so I got 270 total, 30 per slot. So each one should get around 30 balls or discs or whatever they're called. So here's the actual data. Now this frequency table is telling us, hey, out of all those guys that get dropped, how many in one of these slots, how many times does this disc go to 10,000? So if you put it in slot 1, you can expect to see 6 show up, get to 10,000 6 times. Same thing with 2. So if we drop it into slot 2, it's like goes all the way down here and expect it to go all the way down to 10,000 2 times, and so on. So the question asks, basically, what are the probability, or what's the best chance you can possibly have using which slot, and then your second best. So let's copy all this over into Excel, and I'll show you guys what to do. Okay, so here is our data. Now let's identify the best. So the best would just mean, well, which slot gets you 10,000 the most? Well, let's see. So 1 gives it to you 6 times. That's good. 2, only 2, 1, 5, here 8. So 5 gets us the winning $10,000 8 times. So this one would be the best, right? Because there's no other value that's bigger than 8 in our frequency. Okay, so now let's look for the second best. So it looks like it's 6, right? Because the only other one's 5. So this right here would be your second best. Okay, so remember, in this problem, we're trying to figure out the best chance we can possibly have and second best chance of winning the $10,000 based on which slots we used. These are the frequencies or the times that slot will get you to the $10,000. Okay, so this one, remember, we have 30 per slot, so this is going to be our denominator. If I throw my disk into slot 1 30 times, I should approximately get about 6 $10,000 ones. I wish it were that easy, but winning money isn't that easy anymore. So what I'm going to do is the frequency is going to be my numerator, and then I'm going to divide by my 30, right? Because that's how many balls I throw into slot 1, or discs, or whatever they're called. And same thing over here. So the best, here's my numerator, 8, and then I'm going to divide by 30. Alright, so then these would be your answers for that problem. So you can copy them over and make sure you do, they say they want it rounded to the nearest thousandth, so you would just throw those in there like that. Okay, yet another Dungeons and Dragons game. This one right here is a little simpler. So all we want to do is we want to roll it 100 times, choose the histogram that represents this experiment. So here are all the different histograms. All we really need to do is throw it into Excel. Let's throw our little guy here. Okay, and then simply just make a histogram. Now, it's a frequency distribution, so you know, you can do this a few different ways. What I'm going to do is I'm just going to highlight all of my frequencies. So just the frequencies, and you'll see why in just a second. And then I'm just going to click on this. So here we go. I just made myself a basically like a histogram, or just a chart. Should be a better one, not the. So here's some charts and so on. Usually they show more options on this. I don't know. Mine's just kind of weird because it's on a Mac or something. I don't know. But if you just select those data points and then you click on this chart, it shouldn't be too hard to match this up with the correct answer. So what I usually like to do is I usually pick out the first few numbers. So like let's just say the first few frequencies. So 1, 2, 3, 4, 5. So these are the numbers that are showing up or whatnot. Well, this one's 4, and then 8, 8, and then 6, 3. So 4, 8, 8, 6, 3. And let's check this out. So this one, the first number is 2, so that's not right. Here, the first number is 2, that's not right either. We're looking for 4. Here, okay, well, this was easy. So it would be this one. Oh, no, I already did it. So you click this and hit try again. Because see, this is 4, 8, 8, 6, 3. So that was the same as our chart we had before. Okay. So here, this is just another concept type question. Assuming the 20-sided die in the previous question is fair, describe the shape of the distribution over 1,000 more trials. So now remember, this gets into the law of greater numbers, where you know, if you think about it, if you take a single fair coin, and if you flip the coin a very large number of times, the chance that you get heads should be the same, or the total outcomes where you have heads should be right around the same number of outcomes you have tails, right? It should be, you should be extremely close to 50% for heads and for tails. So this should be the same thing, right? If we're assuming that this die is fair, well then each side should appear roughly the same amount of times. Well, remember, if we're thinking about a frequency distribution, if all of your frequencies are right around the same, what kind of distribution are we talking about? Well, it's uniform. Because remember, uniform, think of it like a baseball. Think of it like a baseball team. They all wear the same uniform, so that means that they're all the same. Okay, and that's really all that. Oh, well, actually, let's talk about this last one. So this one is kind of fun too. So I don't know why all of a sudden eMath started going all towards video games and such, but let's just read this problem. You and your friends are designing a video game that uses random number generators to determine non-player character damage outputs. Okay, so one of the NPCs we're designing, Biff, so it gives us the name, has an output output range of the integers from 18 to 32. What's the theoretical probability that one of Biff's attack will strike from 19 to 32? Now, a lot of these I've already done them for, but let's figure this one out. Okay, so our damage outputs, it says, are from 18 to 32. Okay, so 18 to 32. Now remember that counting trick I told you, right? Let's find our range. Our range is simply the large number, so 32 minus 18. Okay, now just add 1 to it. So this guy plus 1. So we have 15 total numbers, right? Okay? So that means that between 18 and 32, there's 15 total different outputs that we can have that'll be including these numbers. Okay? So now, what it's asking for is it's saying, what is the theoretical probability that one of Biff's attack will strike from 19 to 32? Okay, so what's the only number that they're excluding from this list? Well, it's only one number, and that's 18. So basically it's saying, alright, well, what's the probability that it'll use these other 14 outputs? So the other 14 outputs excluding 18. Well, that just means this, right? So if there's 14 total, or there's 15 total different outputs, and we're using 14 of those, the probability that it would be one of those would just be your 14 divided by the total outputs. So 93% approximately, and that's what I put there. Okay, so that's that one. So that's all of 6. So now we get into more of the probability of events, and then some rules here in a second. Okay. So the first couple ones are pretty simple. They're all about sample spaces. In fact, I think most of them are sample spaces until we get all the way down to question 7. Yeah, there's 14 questions in this one. That's a good deal more than we're used to. Okay, so first things first. So here, let's think about this. So it says, of the list below, what are possible outcomes of the sum? So think of this. Remember, it's the sum, not just the face values, but the sums of rolling 2 6-sided dice. So in other words, if I have 2 dice and I roll both of them, one is a 2, like one side is a 2 and the other one's a 3, I sum them together and I get 5. So we just select all that apply. Oh wow, 5 is the first one. Okay, so what are some possible outcomes of the sum? Well, 5, well that's, like I said, it's 2 plus 3. Those are definite. Like, those can definitely occur on a 6-sided dice, right? So this one's 1. Now 2. 2 is also 1, right? Because if I roll 2 1s, 1 plus 1 is 2. Now 8 is also 1, because if I roll 4 plus 4, or 2 4s, it's 8. And of course 7 is 1. Now 1. Now, if this is a 6-sided dice, remember they're only numbered 1 through 6. So in order for me to get a 1, at least one of the dice has to be a 0. Well, that can't occur. So 1 is not possible for the sum of 2 6-sided dice. And same thing for 13 too. What's the maximum number we can get with 2 6-sided dice? Well, roll 2 6s. That's 12. So 1 and 13 are not possible. And that's exactly what we got here. Okay, so now let's do a sample space problem. So these guys are can be pretty annoying, but they're not way too terrible. So here we just have some tiles numbered 1 through 11, and we want to list the sample space S. Okay, so in a sample space is going to look something like this. You're going to have these curly braces around it. The curly braces just means that it's a list full of elements, full of total outcomes or elements. So this guy right here would be like an array, or a matrix column, or something matrix, and then this is just a sequence. But in statistics, when we're talking about sample spaces, we list the sample spaces in these curly braces. So this guy right here would be our sample space S. Okay, and now it gets a little more difficult. So here we have an example of 52 poker playing cards. And actually, you know what? This one isn't as difficult as the last problem, so I'm going to do the last problem, or this next one, because this one you guys can do on your own. But in this one you could too, even though it's kind of annoying. Like you can see these sample spaces get pretty big. But this one right here was probably the one that I found the most annoying. But here you have some company is going to do a holiday party and they're going to determine what kind of food they're going to cater. So they have salads, green beans, breadsticks, chicken, pot roast, and ice cream. So what they want to do is they want to choose 3 options at random without choosing the same item more than once. And in this case, order does not matter. For example, SBI is the same as SIB, BIS, BSI, ISB, or IBS. So you might look at this and be like, what the heck? How do I even start this? Well, here, I can help at least a little bit with a nice procedure if you want to do this procedurally. I mean, you could look at it and go like, well, I know which one's definitely, not going to be this one, not going to be this one. It's got to be a pretty long one, so maybe the longest one. You could do that guesswork. Of course, that's cool, but, there's always the possibility of getting that wrong. So why not try this way? Okay, so S. So I'm just going to start listing the different types of foods. So salads, and then here, green beans is my next one. So green beans and now breadsticks, chicken, and pot roast, and then ice cream. And now this process can get pretty annoying too, but at least this one is a little easier to see. Okay, so in each one of these, I need to choose random subsets of 3 of each one of these values. So I'm just going to mark them with X below them, and then on the right side, I'm going to say, I don't know, the foods, I guess, the foods you choose or whatnot. Okay, so let's say I have a salad, I have the G, so the green beans, and I have the B, whatever that was, breadsticks. Okay, so these are my first 3 foods. So I'm going to have salad and green beans and bread. Okay, so that's my first 3. And now just go through and make sure you don't have any of the same combinations that you had before up here. So see, I have the 3 X's below S, G, and B. I can't have the 3 X's here anymore. So I leave 1 X at S, and then I put 1 X below B, and then I just go right to the next one at C. Okay? So now just keep doing this. So S, C, P, X, P, I, and now I've almost got all of them right or got quite a few of them for S, but I'm missing some X's here. So X, X, X. This is also 1, right? So S, B, P. Actually, it might be easier to see this first. This one. Okay, so I don't have this one, right? And then I don't have this one. So make sure you do all of them just kind of systematically here. X, X, and then I. Okay, so now I have S here. I already have SBC, right? So now I just need this one here. Just keep going through it. Make sure you don't have any of the same X's in the same place. So you can have 2, right? But if I have any of these matching, any of these rows matching, then that's a bad thing. So X, and then here now, I already have this one, right? So I need to put them over here. And then I believe that is everything for S. Okay, so now what are these? This is S, B, C, and then S, SCP, SPI, SGC. Okay, so see, there's no copies yet, right? S, GP, and then SGI, SBP, and then SBI. I mean, you can see this is a pretty annoying process. SPI or SCI, and then that's it for my S's. So now what I'm going to do is I'm going to start with G, right? Because if I use any more S's, I'm going to have a copy of something. So there should be what, like 8 of these, 10 of them. Yeah, 10. So there's 10 of these guys. And then you just keep on going through. So these are all my S's. Now I start with, at least I think this is all the S's. Sometimes it can get confusing. Here's G. So there's my G, and then you just keep going through, right? And so on. Keep going. And until you finish all the way through. So here, you should see, you should have most all of them down now. So this is all the S's. Now I have G, B, C. Then I have G, B, P, G, B, I. And then G, C, P, G, P, I. Okay, so that should be all. That should be on all of these guys. Okay, and then the last one, last few, X, 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 and then finally the last one. So this would be B, CP, B, B, CI, and then B, PI, and then finally CPI. Okay, so all of these guys, so there's 19 of them. It might be missing one, I'm not sure. But once you see this pattern and you have enough of them here, as you can see, they're kind of long and annoying, and it's hard to look back and see what you did. But if you follow the systematic way pretty well, you should be okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so it's definitely this one. I must just be missing one. But here, we definitely have closer to 20 than we do this. So this one must be missing some of our combinations. So we're evidently missing one as well. But we have definitely this first one is the sample space. So that's what I would click. And you can go through and do that systematically, or you could just think about, well, which one of these like are they missing from each of these three? But at least that was the way that I did it. Okay, and this question right here, this one's pretty simple. Remember that in a like a probability chart like this, if we're looking at weather effect, and if it's not thunderstorming and it's not raining and it's not partly cloudy, it's going to be sunny. So the probability should sum up to 100%. So all that we're missing here is 100% minus these guys, and we'll find our sunny. So I just take this up here, copy it over. Looks kind of nasty, but you know, whatever. So let's sum this. So these are just our probabilities. So just sum these guys up. Okay, so 86%. So if we do our 1 minus the 86%, we get 14%. So that's the only one that's missing. So it'd be our So you can see that this isn't really all that bad, but you just hit 14%. Okay? And now these are just pretty much how well can you read this chart. So like if you say a survey of 34 high school students and teachers asked their cell phone plan included unlimited or limited data. So now it's going to ask you, say, hey, let one of these events be A, and then find the probability of this event happening. So we say event A is that you randomly select some student and they have unlimited data plan. So this is, or not even just a student, it's a person. So here we have there are students, there are teachers, and then total. And then we have unlimited data plan, limited, and then all of the totals. So now if we want to find, we pull one random person out, what's the chance that they have unlimited? So it doesn't matter if they're a student or a teacher. So we can use any of these 9 people. So you pull one of those 9 people out is what we want. Out of the total, so out of everybody, so 34. So your answer would be you want to pull the 9 people out of the 34. So it's a probability of pulling exactly one person out. So then that's really how these go. Those are really single events. But the next homework gets slightly more complicated because when we start talking about using multiple events. So that's when we get into these probability rules. Okay. So first things first, we're given a pie chart of insurance company clients by race. So we have African American, we have other, we have Hispanic, Caucasian, and then we have Asian American. So this is just a small little pie chart. It's kind of hard to see the probabilities, so it's kind of funny looking, I guess. But you might have to do a tad bit of squinting for this problem. Okay, so here we have event A, and we're saying, okay, event A is a randomly selected client that is not African American. So find the probability of this happening. Okay, so we see that African American probability of selecting just one person African American is 26.5%. So we want A to be the probability that this does not happen. Okay, so now this becomes slightly more tricky. Okay, oh, dang it, didn't mean to click that. Okay, so we say that 26.5% is the probability of selecting African American. So let's throw that into Excel. So it would be 0.265. This would be 26.5%. And that would be the probability of selecting African American. So if we want to not select African American, this just means the complement of this, right? So remember, complement, so if this is our probability, or this is our event A, we want not A. So not A would just be, well, 1 minus the probability of A. Right? So if we're saying A is African American, 1 minus PA would be not A. Right? So just the complement. So we have 1 minus our 26.5%, and we get 73.5%, which was this answer, and that was correct. Okay, so now it's going to get a little more complicated. So here we have 2 different events, A and B, and we say that randomly selected client is African American, or B is selected is Caucasian. So what's the probability of A or B? So in other words, if we're pulling one person out, what's the probability that they are either African American or Caucasian? So remember, in one of the rules of probability, the sum of probabilities, or the summing rule, or union rule, is when you have probability of A or B, this is equal to probability of A plus probability of B minus probability of A, should be like union or intersection B. So pretend that N is an intersection. So this is the formula, right? But if we know that probability, if we know that A and B do not have an intersection or not mutually exclusive, or are, sorry. If we know that probability A and B are mutually exclusive, well then we know that they aren't going to have any kind of intersection, right? So this just means that your probability of A and your B, they don't have any kind of an intersection together. So these guys don't have anything to do with each other, right? Okay. So probability of A we're saying is randomly selecting African American, and then B is randomly selecting Caucasian. So should there be an intersection in this? Well, what would the intersection be? Well, somebody that's African American and Caucasian. So in this case, that really can't happen. If you have some African American in you, you're African American, and if you're Caucasian, then you're Caucasian. So here we're saying there is no intersection, right? So then this would just be simply this. Your probability of, let's say, African American and then Caucasian. This is, African American is, again, still the 26.5%. So we have the 0.265. And then Caucasian, we have 19%, so that would be 0.19. Okay, so then the probability of African American or Caucasian is simply going to be this guy plus this guy. And there we go, 0.455. Okay? So now it gets a little more difficult. So here we're saying let A be a randomly selected client that is Hispanic, and let B be a randomly selected client who is categorized as other. So if two clients, now two, are randomly selected simultaneously, what is the probability of A and B? So in other words, probability of A and B is saying, okay, those two that we have to select, one of them has to be other, and the other has to be Hispanic. Okay, so this just means that one has to be Hispanic, one has to be other. So let's find the probabilities of these. So the probability of Hispanic is 28% and other is 13%. So 0.28, 0.13. Okay. So we want to find probability of A and B. So both of these occurring. So now, if the two events are independent, probability of A times B, or should be 0. But in this case, these guys aren't really considered those kind of events. So simply, if we want to find, hey, we're going to pick two different people, one has to be Hispanic, one has to be other, you can think of it like this. So I want this event and I want this event to happen. Well, one of them is 28%, so 0.28, and the other one is 0.13. So now when you're doing an intersection, you're doing multiplication. So it'd be your 28% times your 13%. So this would just be equal to this guy times this guy. Right, so this just is saying that, hey, the first guy I pulled out is Hispanic, the second guy pulled out is other. So then the probability of this kind of event happening is around 3%, so pretty small. Okay, and now it says three clients are chosen at random. What is the probability that all three of them are not Hispanic? Okay, so now it's getting pretty tough. Okay, so first off, we need to find the probability that one is not Hispanic, and then we have a certain rule for applying it to the other ones. Okay, so probability of Hispanic is still the 28%, right? So now, not Hispanic, anytime you see a not, think complement, right? So it's just going to be 1 minus 0.28. So this is the probability of someone being not Hispanic. So now if we're pulling three people out, this is person 1, this is person 2, and this is person 3. So we want them all to be not Hispanic. So not Hispanic, and then, not Hispanic, not Hispanic. Okay, so the probability of not Hispanic was 72%. So just continue to copy this along the board. Oops, it doesn't like that. Because there we go. Okay. So 72%, 72%, 72%. Now, if we're saying the probability that all three of them are not Hispanic, are we talking about a sum here? Are we talking about a union? Or are we talking about intersection? Well, if we're saying all three of them must have a characteristic, or in this case, race, then that means that we pull the three people out, one must be Hispanic, not Hispanic, this one cannot be Hispanic, and this one cannot be Hispanic. So it's not Hispanic and not Hispanic and not Hispanic. So in other words, we're going to do multiplication, right? So this just means probability of not Hispanic and not Hispanic and not Hispanic. Okay, so this is just, you can do this times this times this. Or you could also do, so that would be how you would find the probability not Hispanic. Could also be, click on this one and then to the third power. Same thing. Okay. Now this gets a little more complicated here too. So if three clients are chosen at random, what is the probability that at least one of them falls into the other category? Okay. So now, here we go. What's probability of other again? Okay, probability of other is 13%? Yeah, 13%. Okay, so this is 0.13. So now we're saying three clients are chosen simultaneously at random. What is the probability that at least one of them falls into the other category? Okay, so at least one. So that would look like this, right? So let's just say A is this event. So probability of A is greater than or equal to 1, right? So this is just saying, hey, A is the event that we get at least one person that falls into the other category. So that's what our A is. So this is the probability that A has at least one. So this, you could split it up into a few different cases, say, okay, what's the probability that we have exactly 1? Probability we have exactly 2. Probability we have exactly 3. Sum all those guys up. But for me, the fastest way to do this would be complement. And I'll show you why. So probability of at least 1 can also be 1 minus the probability of none. So this is just saying, hey, here this is at least 1, at least 2, at least 3. This is just saying, okay, set it equal to 0 and subtract this from 1. So it's like kind of like the opposite, but it's basically every other possible thing that can happen instead. So that would be what I would suggest, is try doing it through the complement. So let's find the probability that we find exactly exactly 0 of them falling in the other category. So this means in all three, so remember we're still pulling out 3 people, we get not other, not other, not other, right? Because if we get at least one other, then this probability of x being 0 or sorry, a, that wouldn't be satisfied. So this means that here, take our other, 1 minus our other. Okay, so 0.87. So this would be the probability that we get any other race other than other. Okay, so then the probability of a is equal to 0 would just be 0.87 raised to the 3rd power, right? This would be you get a not other, and you get a not other, and you get a not other, right? So then the complement of this would just be 1 minus probability of 3 not others. And then this would be your answer. So 34% would be you get at least one other. So like I said, it can get pretty complicated. So, you know, just try practicing all of this and try getting it through. I know it seems kind of strange, like I'm throwing out like completely random things, and you might be like, "Whoa, how in the world are you doing this?" But if you read through the homework on Loganita, and you're doing this stuff over and over again, you will it'll become easier for you. These last couple ones are mostly just concept. This guy right here can be kind of a nuisance to fill out, but it's basically no different than the problems we just did. But like, just try to remember the rules, like difference between like independent events and mutually exclusive. So if we're saying A and B are independent events with probability of A equals 0.2 and probability of B 0.2, find probability of A or B. Well, if these are independent events and we're finding probability of A or B, they aren't mutually exclusive, which means that they will have an intersection. So in this case here, the problem would simply be, so if A is 0.2, probability of A, sorry. So probability of A is 0.2, and probability of B is also 0.2. Well, then what would our probability of A or B be? Well, remember the formula I wrote up there was probability of A or B, or that weird symbol, is equal to probability of A plus probability of B minus probability of A and B, so their intersection. But remember, unless or if A and B are mutually exclusive, then probability of A and B equals 0. But it doesn't say that they are mutually exclusive. In fact, it's the exact opposite. If something is independent, it implies that it is not mutually exclusive. So in other words, there will be an intersection. So how do we find probability of A and B? Well, if they're independent, if two events are independent, so if independent, then probability of A and B simply equal to the probability of A times probability B. So if they're independent, we have this dude. Okay, so in other words, probability of A and B, so we have this. So all you have to do is find this. Well, what's 0.2 times 0.2? It's 0.04. So you do this guy plus this guy minus this guy times this guy. And you end up with 0.36, right? So all I did was the formula. I did probability of A plus probability of B minus probability of their intersection, which if they are independent, it's just simply multiplication. Okay? And that's pretty much everything I wanted to go over. If you need help with any of the other homework, please let me know. And I'd be more than happy to go over some of these with you, either during my office hours or during the mile, or you could send me an email about them. But other than that, have a nice night.